Hi, today we are going to discuss about mass and weight. Okay, so I'm going to go through some of these contents a bit fast. Okay, but so let's start. Okay, so for the first part, I want you to look at these few diagrams and what difference do you notice in the instruments shown. Okay, you should observe that there's let me change. Okay, here. Okay, there are generally two types of measuring instruments. You can see the first type is you put something on it, right? And then you can see that when you put something on it, it presses the platform down, and that force of pressing down give the weight. So that's this type of instruments. Okay. Also, this is a spring balance. It also works similar because you will hang something there, right? Okay, then you have the load here. So again, it is like pulling something down. Okay, so this is the first type of instrument compared to the second type, where you can see there generally two pens for you to compare. So you put something on one side, you put another thing, maybe okay, of different materials on another side. If it balance, then that means you can see that they weighs the same, right? This is similar, except that you can't see the balancing masses clearly, but it is shown here. So this thing can be adjusted left and right so that you can balance this particular beam. And then this also is a traditional Chinese weighing balance, typically used for herbs. Again, you can see you have a balance here, and you changes the balancing of this beam, okay, by adjusting this particular pivot. So the herb, you put it on the other pen, and then once it's balanced, you can see that, well, there's a certain way of calculating the mass, okay, as compared to this, right? So that's instrument. So you can see two types of instrument. One is by placing the object directly, and then the other one involve comparing with a known mass. Like in this case, this is the known mass, a known mass, and compare with another known mass, right? So that's about all for this picture. Now, for mass, okay, mass is defined as the amount of matter in the body. Matter refers to the atoms, molecules, so on and so forth. Okay, so the amount of matter in the body. The unit for mass is kilogram. Okay, other unit could be gram. Of course, the other prefixes also includes such as milligram, also possible, right? The prefixes that you have learned in term 1. Weight, however, uses a different unit. Usually when you encounter your weight, like, okay, how much do you weight? You say 70 kilogram, 50 kilogram, right? But in physics, kilogram is not the unit for weight. Weight is considered as a force in physics, and force have a unit of Newton. Okay, if this is something new to you, please remember, okay, Newton is the unit for force, and the symbol is a capital N. Okay, so take note of that. We will learn about Newton later on. So for now, just remember this is the SI unit. This SI, the others are also units for mass, okay, but not the SI. Okay, only kilogram is the SI units for mass. The SI unit for force is Newton. Okay, of course there are other way of expressing, okay, but Newton is the SI unit. Now the next thing is gravitational field. What is a gravitational field? Okay, I want you to imagine if you are on the surface of the earth. Let's say we look at this picture, okay, and you have a man, let's say, okay, you weigh 50, oops, okay, okay, let's say you weigh, why is it like this, 500, oops, I think I chose the wrong tool. Okay, let's say you weigh 500 newtons on the surface. Okay, then you go up to a tall building. Okay, how much will your weight be? A tall building, or let's say a 12-story building. Okay, you will still weigh 500 newtons. Okay, and that means the weight in both cases, whether you're on the surface or on the top of a building, your weight is the same. And how do we consider this thing called weight? Okay, in physics they have this particular idea called a gravitational field. A gravitational field means that if you have a mass in the field, the mass will experience a force, a gravitational force. Okay, so in a field, a mass has a weight. Okay, so if your weight is the same as in these two cases, at the bottom on the surface of the earth and as well as on top of a tall building, you have the same weight, then we say that the field here is the same as the field here. They have the same field, gravitational field. Okay, yeah. So of course, gravitational field is not always the same. Okay, it's only the same in this situation because you are talking about a very small difference in height. Okay, a difference of 12 stories is not considered a lot. Okay, in the context of the size of the earth. But if you were to look at the earth as the entire object, you can see that gravitational field is not constant. Okay, but we do not need to worry about this for the moment. So for your case, okay, IGCSE, just remember your gravitational field is constant. Okay, constant, right? Okay, and so with that constant, we need to have a quantity, right? A quantity to describe the gravitational field. So what is the quantity that will be used? It is this thing called the field strength. Okay, the gravitational field strength. So this is the quantity that we use to describe the strength, the magnitude of the gravitational field. Okay, and the symbol that we use to describe this gravitational field strength is G, and you will find it to be very familiar because this is the usual 9.81. Okay, remember previously we used this unit, meter per second square. Okay, but in this chapter, when we are talking about field strength, the units we use is Newton per kilogram. Okay, you may be a bit confused here. Okay, first of all, these two units represents different quantity. The first unit here refers to acceleration, right? Okay, the second unit here represents field strength. Of course, due to certain reasons, they have the same value. Okay, they have the same value, but if you're talking about field strength, you should use this unit. What does this unit means? Seeing that this is 9.81 Newton per kilogram, it means that if I have a mass of 1 kilogram, the weight would be 9.81 Newton. For every kilogram, the weight is 9.81. Okay, so if I have 2 kilogram, the mass would be twice of 9.81, which is 19.62 Newton, so on and so forth. That is the meaning. So a field strength, you can see from here, it describes how strong the field is for 1 kilogram mass. Okay, so we always say that 1 kilogram mass, sometimes we refer it to unit mass because unit refers to 1, right? So let me summarize. It's a bit confusing for this idea of gravitational field, but a gravitational field is a region, okay, that will tells you how strong the gravity is. To describe this gravitational field, we use the field strength, okay, the gravitational field strength. And the gravitational field strength on the surface of the earth has a value of 9.81 Newton per kilogram, meaning every 1 kilogram it has a weight of force of 9.81 newtons. If your mass is 50 kilogram, then your weight would be 50 times 9.81. Do you see it? Because for every 1 kilogram, the weight is 9.81. If you are 50 kilogram, then your weight would be 50 times 9.81. Okay, so that will give you a value of 9.81 times 50. Okay, 490.5 Newton. Don't get the units wrong, because here we are talking about the weight, okay, as compared to here the mass, right? So this is what I meant by weight in terms of the gravitational field strength G. Right, okay, let's do some simple calculation example. A bicycle has a mass of 12 kilogram. What is the weight of the bicycle on Earth? Okay, so we have this formula, W equal to mg. That comes from here, right? For every 1 kilogram, you have a weight of 9.81. So let me write it down here. This is the formula. Okay, so the weight can be calculated by taking the product of the mass multiplied by the gravitational field strength. So on Earth is 9.81, but if you're talking on another planet or the moon, it will have a different value. Okay. So here, let's continue with this example. 12 kilogram times the gravitational field strength. Okay, this is not gram. Okay, it's a gravitational field strength, because here we have a formula. So this 9.81, multiply them together, you will have 9.81 times 12, 118 Newton. Okay, I round off to 3 significant figures, so I ignore away the 0.72 at the end. Okay, let me elaborate a little bit on this, because sometimes, and it is quite often, that the mass could be given in another unit. So let's say I have a small book, and the book is 300 gram. Okay, now you can see it's a little bit different in the sense that here I have kilogram and here I have gram. So remember, in physics, it is very common for you to need to convert units so that you can get the answer correctly. The trick is, okay, if you're not sure, always convert to SI unit. Always convert to SI unit. Okay. So here, instead of writing as 300 grams, I convert it to SI unit, and that will be 0.3 kilogram. Okay, I include the 20 to make it 3 significant figures. Okay, always be mindful of your significant figures. So once I have my mass in SI units, then I could calculate the weight using the same formula, mass times the gravitational field strength. Okay, and that will give me 0.3 multiplied by 9.81. 2.94 unit is, okay, I give you 3 seconds, unit is 321 Newton. Okay, so that's the answer. Example number 2. Okay, an object A of mass 5 kg weighs 49 Newton on Earth. Well, you can calculate that yourself. Okay, just as a practice to verify that it's correct, 5 times 9.81. That's how you calculate. So if you press your calculator, you get 49 newtons, right? Okay, so well, that's beside the point, just some fun calculations. Describe the change, okay, if any, of the weight of A on the moon. Okay, first important thing, the weight. Will it be different or the same? 3 seconds. 3, 2, 1. Okay, it will be different because weight depends on the gravitational field strength. And the field strength is different on different locations. Okay, on the Earth, on the surface of the Earth, we take it as 9.81, but if you are talking about somewhere else on Earth, like in a satellite orbit, it will have a different value, right? So on the moon, it also have a different value. You do not need to know what the value is, but we know, all of us know that on the moon, the gravity is lower than Earth, right? So if the So what we commonly understand as gravity lower, we actually what we mean is the gravitational field strength is lower. Okay, on the moon. So with this idea, the gravitational field strength is lower on the moon, how will it affect the weight of A? Will it be more than 49, less than 49, or equal? 10 seconds. Okay, so here I got a symbol G, refers to the field strength, with a subscript of M, refers to the moon, right? So the mass is still the same, no change, and the gravitational field strength is smaller. So if you have a number, same number multiplied by a smaller number, then definitely this will be a smaller number, right? Yeah, okay. So smaller number. So that means the weight will be less on the moon. Okay. So it will be less than 49 newtons. Okay, so here we do not need to know about the exact value. I just want to know the change. Okay, change means will it be bigger or smaller or remains the same. Okay, so again, be specific. Don't say it is different. Difference is not specific enough. You need to be specific, stating whether it's more or less. Okay, so the answer here is less. Example 3. Okay, I have 3 objects. Okay, A and B are made of the same materials but different size. So compare the mass of A and B. Which one have a bigger mass? Easy. 3 seconds. 1, 2, 3. Okay. B has a bigger mass. Why? For the same material, the larger the volume, the higher the mass. That one is common sense, right? Okay. How about C? B and C. Different materials but same volume. Okay. Not conclusive, we wouldn't know. Okay, but we know for sure that the mass are different. That's all we can say from here, unless we know a little bit more information about B and C. Otherwise, we can only say that the mass are different. Alright, any questions? Okay. And lastly, well, let's go back to the image at the start of this note, measuring mass and weight. So now you can see that instruments like this, okay, where you put something on a pen and then it immediately compresses the scale and then to give you a reading. This measure what? Give you a clue, mass or weight. Okay, I give you 10 seconds, think about this. If it's weight, that means it will be different if you move to a different location, right? Because weight can be different, but mass will always be constant. Reason is because mass refers to the amount of metal in a body, and metal do not change, right? Okay, you have a ball, you bring it to the moon, it's still the same ball. So the metal do not change, so mass do not change. Okay, but weight changes because weight depends on not just the mass, but it also depends on the gravitational field strength. So 2 factors affect the value of the weight. It is the mass and the gravitational field strength. So if we talk about the same object, then the mass do not change. So what affects the weight would be entirely on the gravitational field strength, right? So this type of instrument and this, they measures weight. Okay, they measures weight because you can see that this thing, the object will become heavy if the field strength is more. So it will compress this thing down because the gravity pulls it down, and it will compress the spring in the instrument, which will give you a reading. Instrument like this, they measure mass. Why? Because they compare with known masses. So whether I do this on the surface of the earth or on the surface of the moon, it doesn't make a difference because I have known masses, right? So if let's say I put these 2 blocks of 1 kilogram, so total 2 kilogram, and I put an unknown object on it and it balances, then I know that this for sure is also 2 kilogram because I'm comparing with known masses. Same thing for this and this, they are compared against known masses. So an instruments that compare with known masses measures mass. Okay, so that is what I want you to know. Okay, So what is the difference between an instrument used for measuring mass and for measuring weight? Okay, for mass, okay, instrument will compare against known masses. Okay, then for measuring weight, okay, it's usually just a simple pen, okay, a pen, okay, or a string, okay, so and so forth. You understand my point? Okay, so you only have something, put it on it, whether is it put on it or being pulling it down, like in this case of the spring balance, right? So if you just have one object, that measures weight. And of course, the instrument that you buy from the market, usually when it measures weight, it will still give you kilogram. It will not tell you Newton, because Newton is a very technical unit that is only used in physics, that we don't use in other real daily kind of situations, right? So daily kind of situations we use kilogram. So some of these instruments like this, if you go to C1, you see that the units will be in kilogram. Okay, it's for the ease of use. Okay, so don't take that because it is in kilogram that means this thing measure mass. No, it is not true. Okay, it measures weight, but you can always do conversion right on the spot, because you know for sure this thing must be used on Earth, on the surface of Earth, right? And since we know Earth has a field strength of 9.81, so we will just direct convert it to mass to make it easy for you to measure something, right? Okay, so it is just for convenience that the factory produce it in kilogram. Okay, but this thing in actual fact measures weight, right? So this is all for the content that you need to learn about mass and weight. So what's next will be, you have two exercises. It's coming to the end of the lesson soon. Okay, there's a classwork, there's the multiple choice. Okay, 8 questions I want you to do during this period of time. Okay, and then there's another homework, because today is Wednesday. Okay, I'm giving you this homework, you can take time to do, due on Monday. Okay, the homework I will post it later, you can do it tonight, from tonight onward. Okay, but for the multiple choice you can do it right after you watch this video. All right, thank you very much, goodbye.